Okay, vertical stretch, use the graph of f of x equals the absolute value of x to obtain the graph of 2 times the absolute value of x. And so, again, here we're moving into kind of something different. This is a vertical stretch. And so I'm actually going to delete one of these guys. And we'll do this like we did the previous ones. Let's start with like a table. Okay, so absolute value of x, in this case, since we're just working with real numbers, it just makes the value positive, right? So this is really easy to fill that out. And then the graph is going to look something like this. Remember, that's that V-shaped graph. So that's absolute value of x. Now, if I do 2 times the absolute value of x, I'm basically just doubling the absolute value of x, right? So this would be 6, 4, 2, 0, 2, 4, 6. Okay, so what does that new function look like? I'm doubling. Negative 3 is now at 6. Negative 2 is at 4. Negative 1 is at 2. 1 goes to 2. 2 goes to 4. 3 goes to 6. 4 would go to 8, right? Negative 4 would go to 8. So here's my new graph. So what would you say happened there? That thing got stretched out vertically. Okay, you can imagine if you stretch something vertically, it gets kind of taller and skinnier, right? So this graph has been kind of condensed. It's squished together, skinnier than it was. This is 2 absolute value x. So by doubling our original graph, we got a taller, skinnier version. Okay, 2 absolute value x. It's a vertical stretch. And let's do the same thing, only looking at 1/2 absolute value of x. So again, our absolute value function, we can just quickly draw that out here. And what I'm going to do is I'm going to choose, since I'm going to cut this in half, I'm going to say like some even values here. So absolute value of these, 8, 4, 2, 0, 2, 4, and 8. If I cut those in half, I get 4, 2, 1, 0, 1, 2, 4. Okay. So here's my new graph. Negative 8 goes to 4. Negative 4 goes to 2. Negative 2 goes to 1. Still have 0, 0. 2 goes to 1. 4 goes to 2. 8 goes to 4. And now I've got this. And so here, this is a squished version of my original graph. This is a vertical compression. Notice it's kind of squished down. It's a little bit wider, fatter than it was. And so what was the difference between, I kind of did the same thing. I just multiplied the function by a value. Here it was 2. Here it was a half. And so what causes this to be a stretching thing and this to be a compression? Well, what we end up seeing is it depends on what this value is, of course, whether it's 1/2 or 2, and the kicker is whether it's bigger than 1 or smaller than 1. And so if if that's value, we call that value A. If A is larger than 1, it's stretched vertically. So you get a stretching. That's like 2 stretched it vertically because it was larger than 1. If A is between 0 and 1, it's compressed vertically. And so that's why 1/2 squished that thing down. So you could say that, if you did 3 absolute value x, that would be a vertical stretch. If you did 2/3 absolute value x, that would be a compression because it's between 0 and 1. So this is a stretch. This is a compression. So it all depends on what that value of A is. Okay, so that A value we just used, it was added to the outside of the function. Okay, we took f of x and made it A times f of x, 2 times absolute value, or 1/2 times the absolute value. All right, so what happens if we multiply the argument of the function y equals f of x by some value to get y equals f times a of x? So in other words, let's say I've got like some function f of x equals, say, let's use the square root function. The question is, what if I do some new function, like say 1/2 there, square root of 1/2 x, or maybe 2x, where I'm multiplying the inside value of that function, the argument there, by some value, so 1/2 x or 2x. What does that do to my graph of my function? Okay, well let's look at some more tables here and just kind of explore this a little bit. So let me just do x, and I'm going to do actually a separate table for each one of these. I'm going to say x, square root x, and I'm going to say here, and then also, so 3 different tables. And so for the square root function, what numbers would work well here? We could say square root of 1 is 1, square root of 4 is 2, the square root of 9 is 3, square root of 16 is 4, and 25 would be 5, right? Those are some easy numbers to use inside of a square root function. Now if I try to do the same thing over here on g of x, I can't just plug in like a 1 here and get a nice easy number to take the square root of, right? Because it's going to get multiplied by 1/2. So instead of a 1 here, what if I put a 2 in for x? 1/2 of 2 is 1. The square root of 1 is 1. Okay, what are some other numbers that could do well there? What if I did an 8? What's 1/2 of 8? That's 4. The square root of that is 2. And then, you kind of maybe start to see a pattern here. What about an 18? What's 1/2 of 18? That's 9. Whoops. And then the square root of 9 is 3. Notice 1, 2, 4, 8, 9, 18, 16 is probably going to be a 32. What am I going to get? How about a 4? 1/2 is 16, square root of that's 4, and then maybe a 50 and a 5, right? Kind of see the pattern there. And again, that's because we're multiplying that x value by 1/2. So 1/2 of 2 is 1, square root of that is 1. Okay? And then let's see if we can do sort of the same thing to fill out this table over here, square root of 2x. So again, if we put in a x value 1, that's not going to work well because it's getting doubled, right? But what if I do a 1/2? 2 times a 1/2 is 1. The square root of that is 1. And then what if I do not a 4 here? Remember that x value's got to get doubled. So how about a 2? 2 times 2 is 4. Now the square root of that is 2. And let's see. A 9 works well under a square root, but I can't put a 9 here for x because it's getting doubled. So how about I put a 4.5? Because if I double that, 2 times 4.5 is 9. Square root of that is 3. Now, do you sort of see a pattern here? 1 here is a half here, 4 is a 2, 9, cut that in half, you get 4.5. The 16 is going to be an 8, and then 25 is 12.5. Okay, so great, we got some tables. And you're probably sitting here wondering, what is he doing? What's the point he's trying to make with all these tables? Okay, I just want you to see the pattern here. And kind of the way that this works. Is basically, if I'm going to get, the y values all stayed the same, right? Those are the function values. Here we had 1, 2, 3, 4, 5 on all three of these. The difference is the x columns. And here, if you'll notice, look at this third one. For the y value 1, I needed an x of 1/2. For y value 2, I needed an x value of 2. If you'll compare that to this original table, here I doubled the x value, and didn't it double from here to here? So starting with this square root function, if you double the x, make it a square root 2x, to get the same y values, you've got to cut all your x values in half. Okay? And so, to get the y value 3, you need to take 9 and cut it in half to get 4.5. The same sort of thing happens with this graph right here, this table right here with the 1/2 x, where to get the same y values as the original graph, we needed to double all the x values. And so, you could kind of maybe from that say, well, what if I had maybe another one that was (3x). Okay, if I triple the x value, what do I need to do to my, or if I triple the x here, 3 times x, to get these same y values, what do I need to do to the x value? Well, I need to cut it by 3, right? 1/3, 4/3, 9/3 is 3, and then 16/3. So there's my table for that. And what that actually ends up being is, this is a horizontal compression or a horizontal stretch. And so here's basically the way it works. If we have f of ax, if a is larger than 1, that's a horizontal stretch. If a is between 0 and 1, it's a horizontal compression. Okay, and so that's what that a value does, but it's important to see the connection between kind of the way those tables work out. So let's look at this example right here. It says, use this graph to find the graphs of the following. So here I've got this graph, and don't let the pi scare you. We'll see that's not too bad. We want to find the graphs of 2 times f of x and f of 3x. Okay, so the way that's going to work, and I can probably just do it right here. For my first one, part A, y is 2 times my f of x. So for some given x value, the y value just gets doubled compared to the original graph. So what that means is here my original graph had the point pi halves 1. Okay, my y value is just going to get doubled. That's now pi halves 2. And down here, instead of 3 pi halves negative 1, it's 3 pi halves negative 2. And same thing up here, 5 pi halves 1. And so we end up with this new graph right here. That would be a horizontal compression. Okay. Actually, I misspoke. That's a, sorry, that's a vertical stretch. It's a vertical stretch. All right, so that's f of x. 2 times f of x. Whoops. Okay, let's check out y equals f of 3x. Now, what that means is, again, to get the same y coordinates, if we multiply this x by 3, we need to cut our x's in our table by 1/3. Okay, so my x values basically need to be multiplied by 1/3. Now, what's that going to look like? Okay, so for this point, pi halves 1. To take pi halves and cut it by 1/3 or multiply it by 1/3, we get pi over 6, 1, which is like right here. Okay, and then we've got this point at, that's actually at pi 0 becomes pi over 3, 0. So it's actually like right here. And then we have a point at 3 pi halves negative 1. That actually becomes becomes pi halves negative 1. Multiply it by 1/3, get pi halves. Okay, and you kind of start to see the shape of this thing. If we kind of continue this, we've got a point at 2 pi 0. So that becomes 2/3 pi 0. So 2/3 pi 0 would be like right here. 5 pi halves 1 becomes 5 pi over 6, 1, which is like right here. And then 3 pi 0 becomes pi 0. And so that's my new graph. Actually has a thing right there. And so notice it's been squished down horizontally. Vertically, it's still the same height as the original blue graph, but it's just kind of, it's been squished this way, where that whole up, down, up is kind of just all right here. Okay. And that's really probably the most confusing part of this section is working with those horizontal compressions and stretches. They're kind of the toughest to work with. But the key there, if you double, if you make it 2x, then on your graph you need to cut the x values by a half to get the same y values that you had in the original graph. Clear as mud, right?